All right, let's do an example of an indeterminate power, at least one of the three different types. So we'll take the limit as x approaches 0 from the right of x to the root x. Strange tower function here. So what is happening as x approaches 0? As x approaches 0, well, the base is x itself, so the base is approaching 0, and from the right. And what's the exponent heading towards? The power? Well, the root of something close to 0 is, of course, close to 0. So this is the 0 to the 0th power indeterminate power. All right, so the goal now is to write this as an indeterminate quotient. So that's the difficulty of this situation as opposed to the other two. It's usually more challenging, in a sense, to write this as an indeterminate quotient. But there is a methodology to it, and that is this. I'm going to take the limit as x approaches 0 from the right of the exponential function raised to the natural log of the original function. X to the root x. All right. Looks very strange at first. So first of all, let's be comfortable with the fact that these two are exactly the same. Right? The exponential and the logarithm are inverse functions, so therefore whatever I put inside the logarithm, whatever the logarithm does to this function, the exponential is going to come right around after it and undo it completely and push it right back at the original. So these two limits are totally equivalent because the two functions in here are totally equivalent, although the second one written in a rather strange way. But the advantage of the way this one is written is this. Since the exponential function is continuous, that means the limit of the exponential to some changing object up here is the same as the exponential raised to the limit of that changing object. Okay? So I can slide, because of continuity of the exponential, I can slide the limit inside the exponential function and apply it to the natural log of my original function. Okay? So now this is really what we were going for. I really wanted this situation. It turns out that I'll have to, I want this situation, I want the natural log because of its properties, but to have the same answer as what you would have had from the beginning, I need to re-exponentiate that to get back to the original. But here's what we're going for, and the reason is log properties. One of the properties of natural log is that if you have an exponent or a power on the argument, you can remove that down as a coefficient on the logarithm. So this is now equivalent to e to the limit as x approaches 0 from the right of root x times natural log of x. Right? I'm just removing the root of x. This power, even though it's a variable power, it's a functional power, but I can still remove it down to the front as a coefficient. So the advantage of this is that now I'm dealing with an indeterminate product. I don't have to worry about the indeterminate power anymore and how to deal with it. The natural log alleviates that situation and allows me to apply the limit to an indeterminate product instead. So as x approaches 0, this factor is heading towards 0. As x approaches 0 from the right, this factor is heading towards negative infinity. This is now a 0 times negative infinity indeterminate product. Okay? So I'm going to now take this limit out of context, even though by the end I'll have to re-put it into this exponential function. But at the moment, just to ease the notation here, I want to find the limit of this indeterminate product. Okay? So this indeterminate product I can rewrite algebraically as an indeterminate quotient. So I'll have the natural log of x over 1 over root x. Okay. That should be the same from what we did with the indeterminate product in the previous example. So now we see this is an negative infinity over positive infinity, right? The whole thing, the whole denominator, 1 on root x, positive infinity case. So this is an indeterminate quotient, and I can now finally apply L'Hopital's rule, which is what we're really going for. Okay? So as I apply L'Hopital's rule, I'll have the limit as x approaches 0 from the right of the derivative of natural log is 1 on x. The derivative of 1 on root x, I'm going to view 1 on root x as being x to the negative 1/2 and take its derivative. So I would get negative 1/2 x to the negative 3/2. Okay. If I clean this up algebraically, right, we'll now have the limit as x approaches 0 from the right of, so this negative 1/2, I'll take a reciprocal and I'll get a negative 2. So I'll have a negative 2 in the numerator. 2 here. Right? I still have x down here. This x to the negative 3/2, I can move up as x to the 3/2. Okay. So it should have something like that at first. So now canceling the 3/2 with the first power down here, we'll get the limit as x approaches 0 from the right of negative 2. The 3/2 power cancels the 1 power, and I have a 1/2. I end up with negative 2 root x. So now, as x approaches 0 from the right, I have negative 2 times something approaching 0 is, of course, all approaching 0. Right? So what do we have the limit of? We have the limit of this indeterminate product, which came from the limit of this natural log applied to our original function, which all of this, right, is 0. This needs to be put inside the exponential to be equivalent to the original limit. So at the end, all I need to do is take the exponential function and place into it whatever value I just found, and there is our answer.